A lot of textbooks don't bring up gas-evolving reactions as their own reaction type. The Trail book does, and I like that it does because it gives a nice bit of symmetry when we're discussing gas-evolving reactions, and I can compare them to precipitation reactions. Now, in both cases, what you're having is a product leave the solution. Now, what do I mean by that? In solubility, we said that if it precipitates, two ions actually snap together and they form something that doesn't come apart easily. That forms a solid and it falls out of the solution as a solid. So it's left the solution. In a gas-evolving reaction, we're going to have two things come together, or at least something break off something else, leaving behind a gas molecule. It'll start out as a small individual gas molecule that's dissolved. Eventually it'll find some other gas molecules, make some bubbles, and come to the surface. We've seen some of these in our everyday life, and we've also smelled some of them in our everyday life. Let me point out a couple of them as an example. Now, sulfides, you may not have worked with those quite as much. They give off an H2S gas, so hydrogen sulfide gas. And one example of that reaction would be adding the acid hydrochloric acid to K2S, potassium sulfide. The H pluses are going to replace the Ks, potassiums. You're going to have H2S gas, that's the sulfur stench, come loose as a gas bubble coming to the surface, and you'll have potassium chloride remain dissolved and associated in your solution, and we know that because it says aqueous, and also because we know potassium stays dissolved as potassium ion, and we know that chloride stays dissolved as chloride ion, and they typically don't bind. Now, carbonates and bicarbonates, you have seen this reaction before, I'm sure of it. When you mix carbonates and bicarbonates, you get carbon dioxide gas coming off. And you've done that when you've taken sodium bicarbonate, baking soda, and added vinegar. Well, in this case, the example is showing hydrochloric acid and potassium carbonate giving off water, carbon dioxide, and K2 and KCl, two of the KCls. So you have potassium chloride, again saying dissolved and dissociated. You formed some water, and you've formed some carbon dioxide. Now what you are actually doing is you are taking this carbonic acid, that's H2CO3, and what you're doing is you're knocking loose the water molecule that was sticking to a carbon dioxide molecule. So CO2 and H2O. You can see that those two molecules sticking together would be H2CO3. That's what the carbonic acid molecule is. You've also seen that before because if you shake something with lots of carbonic acid in it, you end up with lots of carbon dioxide coming out of the soft drink that you just shook. That's one of the reasons that a carbonated soft drink tastes a bit more acidic and tart. The carbonic acid that's in it actually our tongue treats it as being acidic and gives it that tartness, but when it pops apart and the carbon dioxide leaves the solution, all that's left behind is a water molecule from that, and so the soda tastes flat, it doesn't have much tartness to it, loses all the sharpness. Now, sulfites and bisulfites, I want to point out that it's the ite. That means that it's not SO4 2 minus, this is SO3 double minus for that ion. Now, it does the exact same thing as the previous reaction. You'll notice that it's actually just about the same thing. It's H2CO3 for the intermediate, and this one's H2SO3 for its intermediate. And you have the same set of products being made, just sulfur instead of carbon. Now, the last one I would want to point out is ammonium. When you're doing the reaction with ammonium, you get an intermediate of ammonium hydroxide. Now, this is worth seeing because it's one that we'll see in laboratory settings pretty often, but it's one you probably haven't seen in everyday life. Ammonium ion and hydroxide ion. It makes sense that these two can stick together. It also makes sense that an ammonia molecule in water might give you some of this substance. And it also makes sense to me that I can work the reaction backward from what I just described and get ammonia gas or dissolved ammonia molecules in water, whichever one you want to think of it as. You can take this molecule, you can hit it with some base, you'll get water molecules. Remember the H plus from over here and the OH minus give us water. We'll have an NH3 left behind, and then the spectator ions, K and Cl, are going to pair up to make potassium chloride, but they're not going to stay together. They're going to be dissolved and dissociated because they are aqueous. That's the kind of thing we're going to be talking about for an ammonium reactant type. Now, with these, I don't think we need to memorize them carefully, but these are good examples to work through, and we will see some gas-evolving reactions in our laboratory work, and like I said, in our everyday lives.